I have here a bundle of DS18B20 one-wire temperature sensors, and I have an Arduino Nano on a breadboard. And of course, I have one wire for the bus. In the end, I want to have 4 of these temperature sensors connected to my Arduino Nano via 2 different one-wire buses. One with phantom power, so really only one wire plus ground, and the other with an additional 5-volt supply line, so in reality 2 wires plus ground. Anyway, before we start wiring up, a little theory about the one-wire bus and why running a one-wire bus from a microcontroller is a wee bit different than running it from, say, a microprocessor. Let's first focus on the data transmission on a one-wire bus. So this is my one-wire bus line, and I have a master and I can have one or several slaves. The bus line is normally high, pulled up to VCC by a resistor. And yeah, I wrote here 4.7K. That's what you find in most data sheets. But maybe later on we will talk a little bit more about the value of that resistor. But 4.7K on a breadboard should work without any problem. Now, when the master wants to transmit something on the line, he simply pulls the line to ground. In olden days that was a bipolar transistor, so that was called open collector. The collector here was open. And nowadays you have a MOSFET in the chips. Vice versa, if the slave wants to transmit something, it pulls the data line down to ground. No problem so far, and each master and slave do have some input buffer or stage when they're just listening to what's going on here. No problem if master and slave pull down the line at the same time. There are no shorts or so the bus is quite robust. Onwards to the elephant in the room, phantom power. So most one-wire devices can be powered not by an explicit connection to VCC, but over the data line. And that's possible in most situations. More about that later. So inside a slave that provides or supports phantom power, the VCC line, if it exists at all, is going via a diode to the internal circuitry. But also the data line is going via a diode to the internal circuitry, and there is a capacitor inside for energy storage. So if you have no VCC, if that is cut off, and as long as the data line is high, the internal capacitor can charge up. And then when the device starts to work, that is to transmit or do whatever it does, it can retrieve the energy from the capacitor. Okay, there's one problem here. Charging up that capacitor via that 4.7K pull-up resistor is not really working. And so the master has to make sure that in specific intervals in all that data stuff going on, it pulls up the data line hard to VCC so that the capacitors in all the slave devices can be charged and the slaves can do their job. Needless to say, if the master is basically providing power to the data line while itself or a slave tries to pull the data line down, yeah, you have disaster. A slave will die or your master will die. Whatever. Anyway, but preventing that is all encoded in the one-wire data protocol, how these different devices communicate with each other. And yeah, we will skip the details on that. This is going into 100 pages of documentation or what. We will just rely that the hardware implementation here and the software implementation here works properly, and that building a short here will never happen. And here comes the reason why there is a little difference in driving that bus considering the used hardware. When you compare driving it with a microcontroller than compared to a microprocessor. You have this totem pole output configuration in most digital devices today. But in a microprocessor, these MOSFETs, they can deliver or sink maybe a milliamp at most, okay? And that's not enough to provide all that power, all that current you need to charge up all these capacitors. So for a microprocessor, usually this MOSFET will be external, and you find that also as an external part in the data sheets of the different one-wire devices you can buy. If you use a microcontroller, the totem pole configuration here in the outputs, it can provide easily 10 milliamps or sink 10 milliamps. So no problem here. I mean, the 10 milliamps are, I think, the limit for the Nano. If you have a Uno, it can provide or sink 20 milliamps. So we actually won't see that external MOSFET here because it's all inside our Nano. And everything here is controlled by the one-wire software library for the Arduino. I guess we have enough now to start up wiring the whole stuff and have a look at the software. So I wired something up here on the board. And that's basically two one-wire buses. The green one is my bus 0 and the yellow one is my bus 1. And each has two of these temperature sensors attached. Note the difference. You cannot see it, but the two connected to my green bus 0, they have ground and 5 volt. So they are not running on parasitic power, but instead they have a direct 5 volt supply. Whereas the two ones I wired to my yellow bus 1, they only have a connection to ground besides their data connection, and they are basically running on parasitic power. And there's a little red bridge from ground to their VCC pin in VCC red, because the datasheet says you should do that if you want to run these things on parasitic power. Now let's have a look what the software is saying. So it's basically always saying, okay, bus 0, sensor 0, 29 degrees Celsius, sensor 1, 29 degrees Celsius, bus 1, sensor 0, 29.5, and sensor 1, 29.0. And if I touch the first sensor on my bus 0, you see the temperature is rising. I touch the second sensor on bus 0, the temperature is rising. Bus 1, sensor 0, temperature rising. bus 1, sensor 1, temperature rising. So, fantastic. Bye. Well, not quite. Let's first have a detailed look on what's on the breadboard and then on the software. On the breadboard, we have our 4 DS18B20 devices. The first two are connected to our bus, one-wire bus 0, to the D2 digital pin of the Nano. The second two are connected to our one-wire bus 1, connected to the D3 pin of the Nano. And both buses are pulled up by a 4.7K resistor. Now on bus 0, our devices are directly powered by 5 volt from the Nano, while on bus 1, our devices are phantom powered and their VCC pin is grounded. And that's actually stated in the datasheet. If you use phantom power, you cannot leave the VCC pin open. You have to connect it to ground. Let's have a look into the datasheet. And there it clearly states when the DS18B20 is used in Parasite power mode, the VDD pin must be connected to ground. I think I called it VCC, whatever. And yeah, that's the schematic for it. You see VDD and ground bound together and connected to ground. And we see here again the external transistor pulling the one-wire bus hard up to 5 volt to provide the phantom power or parasitic power. And the reason for that we can gather from the block diagram. There is a power supply sense on the chip connected to the VDD pin. So the chip actually knows if it runs on direct power or on phantom power and can adjust its behavior accordingly. When it's running on direct power, it doesn't have to wait until the capacitor is charged up to do its stuff. And when that VDD pin is just dangling in the breeze, you might get some leakage current down here, and it might get the impression that it's actually running on direct power while it's actually running on phantom power, and then things might get awry. There's actually not much to the code. We need the one-wire library and the Dallas temperature library. The one-wire library does all the bit banging, and is controlling the pin, while the Dallas temperature library knows all the commands our temperature sensors understand and is basically using the one-wire library to drive the pin. This is basically the simple example from the Dallas temperature library, which I expanded to be able to use several buses and several sensors. So we have 2 one-wire buses, and these one-wire buses are using the digital pins 2 and 3, as I've shown you. We need 2 instances of the one-wire object, which I call buses, and 2 instances of the Dallas temperature library, which I call sensors. And the setup is quite simple. We initialize the serial port so we can see what the thing is doing. And then in a loop over the buses from 0 to 1 in our case, we first initialize the library, the one-wire library, and we just tell her on which pin it is working. And then we set up the Dallas temperature library. First, we tell the temperature Dallas library which one-wire object it should use. Then, begin. It does its internal stuff and initializes the sensors. Then we set the resolution. We are reading out in this example 9 bits resolution temperatures. So the least significant bit is 0.5 degrees Celsius, and the conversion time each of the temperature sensors need is 93.75 milliseconds from the datasheet. We will have a look at the datasheet in a second. And finally, that's not in the simple example, I set the option set wait for conversion false. You can tell the Dallas temperature library to do all the timing and automatically wait in the library itself until such a sensor finishes its business. And that's all for the setup. The loop is also quite simple. So I have here two variables just to count through the buses and to count through the sensors. My outer loop here counts always through the buses 0 to 1. And then I send for one bus a request temperature command. And the Dallas library does all the other stuff and sends the temperature request command to all slaves. And then we'll have to wait. Remember, in the initialization, we said the Dallas temperature library should not wait until all the slaves are finished, doing their temperature stuff. Instead, we do it, delay 250 milliseconds. And then in an inner loop, I loop through all the sensors on the actual bus I'm currently working on. And the Dallas library knows exactly how many devices are on the bus. It determines that when you initialize the library. Side note, if you add or remove devices after initialization from the bus, the library won't know about that. And then the only thing left is to get the temperature for each sensor. So the library sends a get temp command to the slave, and the slave sends back the temperature, and we can print it out. That's all. That information here, how long we have actually to wait until such a temperature sensor is finished with its temperature stuff, that's from the datasheet. And we shall have a look at that now and maybe look at the differences between the B and the S version of the DS18X20. So the 18S20, which I'm not using, has basically plus minus 0.5 degrees Celsius accuracy between minus 10 and plus 85 degrees C, and a fixed 9-bit resolution. While the DS18B20 has basically the same accuracy here, but a programmable resolution from 9 bits to 12 bits. But that's not all. The time, the temperature conversion time, that is the time we had to wait from sending out the signal to all the sensors to do their temperature thing, and until we actually were able to read that data back from them, it's 750 milliseconds for the 18S20 at 9 bits, 0.5 degrees C. While the 18B20 needs for 9-bit conversion, so 0.5 C resolution, only 93.75 milliseconds. And then you can program it, we saw it in the code, to use 10, 11 or 12-bit resolution. And basically the time doubles until we are at 750 milliseconds for 12-bit resolution, and that's 0.0625 degrees C. So that DS18B20 is much faster than the 18S20. In addition, the B version is also a wee bit more precise. So in the range from -10 to 85 degrees, plus minus 0.5 degrees C, that's basically the same like the S version. And from the range of -55 degrees C to 125 degrees C, it's also the same like the S version, plus minus 2 degrees Celsius maximum error. However, the S version does not specify the area between -30 degrees C plus 100 degrees C with plus minus 1% error. Yeah, it's marginal, but it's better specified at that point. And needless to say, if you buy a Chinese sensor, it will almost every time be the 18S20, because the 18S20 is also a lot cheaper than the 18B20. With what we learned so far, I changed and optimized the code a little bit. I mean, first of all, I'm now querying within the setup if a bus is using parasitic power or not. So bus 0 here is not using parasitic power, while bus 1 is using parasitic power. I also increased the resolution to 10 bits. So you see here least significant bit 0.25 degrees Celsius. And I optimized the loop a little bit. Let me turn auto scroll on. Yeah, the lines come now smoothly and there is no hiccup in between a line between bus 0 and bus 1. Otherwise, it works as expected. Yeah, I touch that sensor here, bus 0, sensor 0, temperature increases. Bus 1, sensor 1, temperature increases. Nice. Now, if I remove a sensor, I get an error value here. Okay, so yeah, determining how many devices and what devices are on the bus just happens during these setup things. If you want to requery the bus, you dynamically adding devices or not, you have to go through the setup again, at least parts of it. Yeah, the Dallas library. Let's put that thing back in and yeah, everything's fine again. Now to the elephant in the room. How does the software, the library, know that this is device 0 and device 1 on the bus? Simple answer, it doesn't. If I switch these devices out, and you notice I'm not trying to do that on the parasitic powered bus because, yeah, you know, probably timing, shorts and so, but only on the direct power. And I heat that sensor up now. It's suddenly sensor 1. And this here is sensor 0. So yeah, basically when I built that up and wired it, I just got lucky that this is always 0, 1, 0, 1. There is no way that the software could have known that. And that brings us to addressing specific devices on the bus. Before addressing the addressing issue of devices on the bus, let's have a look on the changes I did to the code. In the setup, I just changed the resolution from 9 bits to 10 bits. So that means we need now 187.5 milliseconds according to the datasheet for temperature conversion. And I also query for each bus if it is using Parasite power mode. The optimization in the loop is also quite simple. I just took our request temperature command from the existing loop in its own loop up front. So basically first I send the request temperature command on all buses to all devices, and then I wait. Yeah, the wait was here before, and then I start querying all the sensors on all the buses. And yeah, that shaves off another few hundred milliseconds in wait, and yeah, it looks nicer. And now onwards to addressing specific devices on a one-wire bus. So in the general description of the DS18B20, you find the sentence, each DS18B20, well, in general, each one-wire device on Earth has a unique 64-bit serial code, which allows multiple DS18B20s or multiple one-wire devices in general to function on the same one-wire bus. 64-bit addressing. Yeah, talk about IPv6. I mean, one-wire bus is been around a long time longer than IPv6, and yeah, we will see how many devices we can actually address. Such a 64-bit device address contains the first most significant byte, an 8-bit CRC. Okay, so we can forget about that. And the least significant byte, it contains the family code of the device, basically what type of device you're dealing with. Yeah, for the 18B20, it's 28 hexadecimal. For the 18S20, it is 10 hexadecimal. And then in the middle, we have a 48-bit really unique serial number within the family, which allows us to address aboutish, if I did my math right, 281 tera devices. Okay, so talk about Internet of Things. I modified the software again so we can see in the setup the 64-bit addresses of the devices. And you see here this is hexadecimal, the 28 that comes out first, which indicates this is an 18B20, or these are 18B20s. And the rest is obviously different and unique for each and every one of them. I also, let me switch auto scroll on. I also changed the manner how I address these devices now. But we will see a little bit more about that inside the code. I've added two more lines to my declaration. The first one, one-wire sensors, simply specifies how many sensors are on every bus. The second one addresses, this is a two-dimensional array, bus and two sensors per bus, to store the 64-bit addresses. So device address is a type that comes out of the Dallas temperature library, and it's basically an 8-byte array. In the setup within the loop that goes over our two buses, I added at the very end another loop that goes over the sensors on the bus, which should be two. I'm a little bit defensive here. I have two conditions here. First, the fixed number 2, and then in addition, I also query the actual number of devices on the bus. And all I do here is I load the actual 64-bit address of a device into my array. That's that statement here. So sensors, we are at the bus, get address, and then is my two-dimensional address array, and then the index of the sensor I need the address of. Yeah, this is passing a pointer down into that method, and it will get filled with the address. And then I have another little loop, yeah, printing out the 8 bytes in hexadecimal, which we saw in, yeah, what the Arduino printed out in the init. There's only a very small change here in the main loop. Instead of get temp C by index, where you simply pass an integer, sensor 0, 1, 2, 3, yeah, depending on which bus we are, I now pass the actual address, the 64-bit address, to a function get temp C. And yeah, the Dallas library explicitly says this function is faster than using the index function. But yeah, that's only if you need to shave off some microseconds or some 100 microseconds, I guess. Yeah, that's all. But what do we do with that? We do know now that each and every one-wire device has a unique 64-bit address, okay? So, yeah, the first byte is only the class, yeah, 28 hexadecimal are our temperature sensors, and the last byte is only a checksum, don't care about that. And in this example, I have 3 devices which have a 48-bit address of 1, 2, and 3. And let's say they are at the left, middle, and right somewhere in my bus, or in my case, in my enclosure, whatever, measuring something. So how can we actually make sure in our software that we are addressing the right sensor when we want, for example, read the left temperature? And there are many strategies, but 2 obvious strategies are: first, read the address of a device and label it. Yeah, make a little breadboard thing, put only 1 device in, print out the address. Yeah, you saw how that's done in the code, and label it. Yeah, put a little paper label on it before you assemble everything. And yeah, then you can, well, hard code, you can make an input procedure that would be more visible and store the addresses yeah, in the EEPROM of your Arduino, but somehow, yeah, transfer that knowledge into the software, and then you are able to, yeah, address the right sensor with the right address. The second approach would be you have to design your hardware, yeah, for example, by using jumpers, so you are able to connect 1 device to the bus at a time, and then do all the labeling and assigning in a special software procedure. Yeah, so for example, you say make something called initialization, and it goes through all the sensors, and then you have some user input saying, okay, that's sensor left, that's sensor middle, that's sensor right. And again, the addresses can be stored in the EEPROM or wherever. And there are a lot more strategies you can come up with, but you need to do this assignment at some point. And yeah, it's additional software effort. But enough about the software. I promised you we will talk about the pull-up resistors too. And the 4.7 case, yeah, you find everywhere in the data sheets. They're absolutely fine as long as you're just working with a dozen devices in one enclosure, or, well, you could even connect some devices via, let's say, 1 or 2 meter, 3 to 6 feet cables to your box, 4.7K will still be okay. However, maybe you might want to put your devices on a, well, few dozen meters of cable, yeah, a few dozen yards, and you want to have a dozen devices on your bus, then 4.7K might be too large a value, and you might want to decrease the value of the pull-up resistor, simply to have a stronger pull-up to overcome all these stray inductances and wire resistances and capacities you introduce in a very geometrically very large bus. And how small can you make that resistor? Well, the answer is again in the data sheet under DC electrical characteristics, not absolute maximum ratings. And there you find a sink current, which is a minimum number, 4 milliamps. And that means that a DS18B20 can sink, that is, pull the bus down at least with 4 milliamps, and you have a maximum of 0.4 volts on the bus. So that's the maximum it can sink, and now we can calculate our minimum resistor value. I switched pictures again so we have a better view of the innards, what's going on. So we were talking in the data sheet about the sink current IL, or I, current L for low, that can flow through here, minimum. And in the data sheet it says 4 milliamps, okay? And 5 volts, our VCC in this example, it's important to know at which voltage you run your bus in that case. At 5 volts divided by 4 milliamps, that gives a 1.25K resistor. That's the minimum value we can use here. Depending on the tolerances you have on your voltage supply and the tolerances of your resistors, you might want to use a 1.3K or 1.4K resistor to be on the safe side. Just to be complete with our 4.7K resistor, 5 volts divided by 4.7K, we have a sink current here of 1.1 milliamp. So we basically can turn up the volume by a factor of 4 almost current-wise on our bus, which makes it much more resilient, okay? And some more remarks on Parasite power, okay, or phantom power. I called it several times in this video. Phantom power is a term you use normally for microphones, but it's the same principle, okay? The datasheet clearly states the use of Parasite power is not recommended for temperatures above 100 degrees Celsius, okay? Because then the additional leakage currents on the chip at these higher temperatures will drain your capacitor that is storing the energy too fast, and the device will simply stop working. I would like to tell you much more about the one-wire bus, the one-wire library, the Dallas temperature library, and the DS18B20, but I think it's enough for today. I left out a whole bunch of things. We haven't explored each and any feature of the Dallas library or even the one-wire library. And we haven't explored not every function of these temperature sensors. For example, you can program them to have a low level and a high level temperature alarm, okay? So they can have a little EEPROM in them where they can store 2 bytes of data. Who would have known? Another thing is we talked a little bit in between about the pull-up resistor, and in larger networks you can make that pull-up resistor smaller so you can get them to work. There are single wire networks out there, buses that span hundreds of meters, and if you believe what's in the internet, hundreds of devices. You won't get such buses up and running just driving the bus with an Arduino and using a pull-up resistor. Yeah, so a lot I haven't covered. If you are interested in something special, yeah, just let me know. Maybe, no promises as always, I come around doing that. But I guess just to build up your first one-wire buses and maybe have a little temperature measurement thingy or whatever with the DS18B20 or 18S20, you know more than enough now. And with that I say bye.